Hello, uh, welcome to the fifth week tutorial session for the NPTEL course of Statistical Mechanics. My name is Parasar, and today we are going to discuss some problems on the microcanonical ensemble formalism of statistical mechanics. So yeah, let's get started with the problems. Yeah, so this problem is is to show is to illustrate the formalism of this microcanonical ensemble, counting states and so on. So it's a simple counting or bookkeeping problem. So in this question, the system at consideration has 5 atoms, and it is given that each of the atoms can be in 3 states whose energies are 0, 1 and 2. So there are 5 such atoms. So each atom has 3 levels, 3 energy levels. And yeah, the system is isolated. So that is where the microcanonical ensemble comes in. So the total energy of the system is fixed, and it is given that this total energy is actually 6. So 6 in some units, in the same units in which these energies are 0, 1, 1 and 2. So now the problem is to find the total number of microstates that are consistent with this macroscopic so even though it's just 5 atoms here, the the total energy of the system. So number of microstates that are consistent with the total energy being equal to 6. Okay, so we can simply try to list all possible or different types of possibilities. So we can for example, we can have 3 atoms with energy 2. Let me just denote these or separate these with commas. So you can have 2, 2, 2, 0, 0, and there will be 5C3 such states. You can select any 3 of the atoms and say that they would be in a state with energy 2. So there are 10 ways of selecting this, and of course there can be this distribution 2, 2, 1, 1 and 0. Yeah, so to select the 0 state or to select the atom which is in a 0 state, there are 5 ways. So that's 5 times, and out of the remaining 4, we can select 2 atoms and say that they would be in the state with energy 1. So that would be so this total would be 30, and so on. We can try to list other possibilities. So we can have 2, 1, 1, 1 and 1. So clearly there are 5 ways of doing this. And is anything else possible? Sorry, yeah, just a minute. Yeah, great. Yeah, so yeah, so we have so far listed these types of possibilities. Is there any other possibility? Okay, so we cannot have 5 ones, so we must have at least one atom with energy in the second state, so let me just say that in a better way. So there must be at least one atom uh, uh, which has an energy equal to 2. So and the and the rest 4 can be partitioned like this: 1 1 1 1, or 2 1 1, or 2 2. Yes, yeah. So yeah, so uh, we have written all the possibilities. Okay, so if we total these, that would be 45. Yeah, so that would not be necessary. Yeah, so the total number of microstates is 45. Yeah, so this problem is just to warm up uh, when it comes to applying the formalism of this microcanonical ensemble. So yeah, so we're going to do more such uh, counting problems and try to apply to some physical systems and see what thermodynamics we get. So yeah, so this week is going to be very interesting because we're going to use the microscopic uh, details of the system. Like we're going to derive uh, or say something about the thermodynamics of systems from the microscopics. So yeah, it's going to be very interesting. Sorry, yeah, sorry about that. Yeah, so let's then look at the next. Sorry, yeah, let me just adjust the mic. Yeah, so yeah, let's look at the second problem. So we have a system of n one-dimensional particles. So these are particles which move only in one direction. So we can say that it is a one-dimensional system, one spatial dimensional system, and it has n particles. So these are all classical particles. I mean, particles obeying or following the laws of classical mechanics. Uh, so there are n of these particles, and each of these particles is in a potential well. So something like this. Yeah, so you might have looked at something like this in what is called a classical solid, ideal classical solid. Uh, there, the particles are trapped in harmonic potential wells, but here the potential wells are they have a different shape. So of course they are still wells in the sense that uh, v of x goes to infinity for mod x going to infinity. So uh, So these potentials trap the particles, and you have to pay some potential energy if you want to move the particle away from this from the mean position. So the only difference from the classical solid, the classical yeah the from the classical solid is that this dispersion is different. So what if there is such a system, and can we say something about the heat capacity of such a system, or temperature uh, energy relation uh, 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 using the microcanonical ensemble formalism. So yeah, we're going to consider an isolated system uh, and try to write its entropy. So yeah, so let's say that the energy of the system is okay, let me just write that the system is isolated, and the energy is between some range E plus delta and E. Okay, and the phase space variables of the system are as follows. So x1 p1, x2 p2, and so on. So these are xi is the it's the position relative to the nth atom's mean position. So yeah, anyway, these are the phase space variables, and we can try to ask what is the volume of this region in the phase space, in the region defined by this statement, that the energy of the system is in between some window. Okay, so let us first try to write the or first express the energy uh, in terms of let me use a different symbol, I mean, just be to be very precise. So yeah, so let us express the energy E in terms of the phase space variables, in terms of these. So the kinetic energy of the particles is simply going to be p squared by 2m for each particle. So the sum is going from 1 to n, and the potential energy is going to be v of xi, but it is given that v of xi is of this form. Yeah. So by the way, so like we discussed, this is a well, this is a potential well. So a is positive, a is a positive number, and n is a positive integer, so that we have this property that the potential is infinity at both plus and minus infinity. So yeah, with that stated, let us try to address this question of the volume of the phase space. So it is or this phase space is, this is a 2n dimensional region, right? This is a 2n dimensional region. Phase space is 2n dimensional region or space, and of course I cannot draw or try to show you something in this 2n dimensional space using a figure here, but schematically if we could draw some directions. So this would be P1, X1, P2, and so on. I mean, that's all I can. That's all I can draw. That's where I should stop. But it has uh, two n orthogonal axes. I mean, we can think of a coordinate system in which there are two n orthogonal axes, and we want to look at the volume enclosed by this equation. Let us denote with cal v. So this is okay. I'm using a different, some fancy v symbol, so that so this is different from the volume of the system. Like even in this problem, it would be a length because it's a one-dimensional system. But even in the even to make sure that there's no confusion with the notation in the future problems, I'm using a different v, some fancy v. This is the volume in the phase space. With energy less than or equal to E. So that would be a two-n dimensional region, and that would have a volume. So what we want, our required phase space volume, we want the volume enclosed between two such surfaces. So we want this cal v of E plus delta minus v of E. So it looks like it would be very difficult to find some exact expression for this v of E, but that is not actually required, as we will see. All we need is how all we need to know is how this cal v of E depends on the dimension of it depends on the number of atoms we have. So we want the dependence on n and E, and in particular how the volume increases with E, and as what power of E in particular. That is what we would actually need for most of the purposes. So let's be more concrete and try to understand that statement. So we can try to look at the points on axes where the surface cuts the axis. So we can look at, let's say, focus on this axis P1 and ask, is there a point on this axis at which the surface cuts this axis? Yes, indeed. So ultimately we would have a bounded volume, and we can ask, when does when is there a solution of the kind P1 0 0 0 0 and so on. So only P1 is non-zero, everything else is zero. That is why this is on the P1 axis, and the answer to that would be, not surprisingly, square root 2me. And we would get a similar story, or we'll have a similar picture for every p-axis. So the surface cuts P1 axis at this point, square root 2me. So there is a similar picture for analogous. Yeah. for P2, P3 and so on till Pn. And then we can similarly ask, where does the surface cut the x-axis, or the axis labeled by coordinates x1, x2 and so on. So if you look at x1 and ask where does this volume or this the surface uh, which is a boundary of the volume cut the x1 axis, that would be at e by a whole to the 1 by n. Right, so at this point every other coordinate is 0, and we have a similar picture for x2, x3 and so on. So uh, so if we just try to imagine this this volume which is given by the region in which the energy function is less than E, so that would have so to speak dimensions in various directions like this. So of course I am only drawing two such directions, but the dimensions of this surface are square root TME, square root 2ME, square root 2ME, so on, square root 2ME, and yeah, this and so on. So like we discussed, this is a 2n dimensional region, and we have uh, some rough idea about the dimension of this surface in these 2n directions. So in n of these directions, its dimension or length is proportional to square root e, and in the 2n other directions its length is proportional to e raised to this exponent 1 over n. So so uh, so just from this basis, so this is just like dimensional analysis, just from this basis we can say that the volume of this region must be proportional to these like the product of these dimensions up to some constant, which depends on of course the number of atoms or the phase space dimension. It depends on that. It of course depends on what potential we have, little n. uh, but apart from this factor, we can just simply write this as uh, square root 2me whole to the n, and e by a whole to the this thing, n by n, capital N by little n. Yeah, oh sorry, here it is, yeah, n over 2. Yeah, so up to some factors, this is going to be e raised to the power half plus 1 by n times n, capital N. So this is the volume enclosed by this surface, or to say this in another way, this is the volume enclosed by the region in which the energy function is less than E. But what we need is a difference of two such volumes. So ultimately what we need is this number of microstates omega as a function of E and N. So this is going to be the volume of the phase space of interest. divided by some dimensionful quantity to make it dimensionless. So that would be typically Planck's constant raised to these some appropriate power. So we have 2n dimensional phase space here. Yeah, so yeah, that would be something like h to the n. So this is the number of microstates. So yeah, is there any question at this point? Okay, so what we yeah, what we'll use next is the power of the thermodynamic limit. So in this limit, in the limit when the number of particles we have is very large, then the phase space dimension would be very large. Then yeah, then when we have a volume like this, so some bounded volume. So let's say V of E, V of E goes as e to the um, so let's just write it as some Zn. Then V of E minus V of or let me V of E plus delta minus V of E is going to be sorry. So that is going to be equal to sorry, this is Zn. Yes, so we have this sort of a expression, and the quantity here is less than 1. So for the kind of n that we encounter in thermodynamic systems like let's say 10 to the 23, or we can say in the limit n going to infinity, this this term here, this factor goes to 0. This goes to 0. So that means that the volume of the shell is to a very high accuracy, is basically equal to the 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 total volume enclosed uh, by the outermost surface. So this is just saying that for very high dimensional regions or volumes, most of the volume is actually in its shell uh, or the region near the surface. So this greatly simplifies things for us. So we can then simply write that the number of microstates is V of E divided by the appropriate dimensionful quantity. So that is going to be so this unknown function alpha multiplied by some constants. I hope I got this right. Yeah. times the most important factor in this equation, 1 by n plus 1 by 2 times capital N. Yeah, so what can we do, or what can we calculate without knowing alpha? So is alpha required to derive, is the knowledge of alpha required? Knowledge of alpha required to derive the thermodynamic properties we need. So the answer is, for most of the thermodynamic quantities, it is not required. It is not of importance to know this to know this function. So only when we actually need the absolute entropy do we need this function alpha. So this is required only for entropy, only for absolute entropy, only for calculating absolute entropy. But for most other thermodynamic quantities or experimentally uh, relevant quantities, the knowledge of alpha, it turns out, is not required, because we are going to take derivatives of this expression with let's say t or v when there's some volume. So yeah, yeah, let me finish writing this. Yeah, so once we get the functional dependence of the number of microstates on E and V volume, if it is applicable, then yeah, most of the thermodynamic quantities can be calculated, like an equation of state or heat capacity, etc. So yeah, so let us now actually uh, crunch the formalism, the microcanonical ensemble formalism. So we have the number of microstates as a function of E and N. So we define the entropy as the logarithm of this quantity. So S of E, or yeah, S of E and N is going to be some logarithm of all these factors, constants, uh, plus n times half plus 1 over n times E. Yeah, so we need the temperature, or the definition of temperature is that it is the partial derivative of entropy with respect to the energy at constant n. So that is why we don't need this alpha in this case, even though we haven't gotten the functional form of alpha. You can get away with it if you want to calculate, let's say, how the energy depends on temperature, or let's say heat capacity. So this is simply going to be n times is something wrong? Oh yeah, so there is yeah, it is log E, sorry, yeah, in this previous step it is ln E. Yeah, so then yeah, so E is going to be, E as a function of T is going to be, or let's say E by N, the energy per particle is going to be T times half plus or half plus 1 over n times t. So when n is equal to 2, that would be the classical solid in one dimension, classical Einstein solid. Sorry, it's just the classical solid in one dimension. So that this would be the Dulong-Petit's law for classical solids in one dimension. Yeah, but here we have a different potential, and this is how this exponent that that determines the potential enters the heat capacity. So, or heat capacity is heat capacity per particle, or specific heat capacity per particle. So CV by n in this case is uh, yeah, 1 by 2 plus half 1 by 2 plus 1 over n. Yeah, this is of course when kb is 1. So we have set kb to 1, and the entropy definition is just a logarithm. It doesn't involve kb, so the entropy in this units is dimensionless. So yeah, then this is simply the heat capacity per particle. Okay, so yeah, so this is one example where we calculated the phase space volume to find the number of microstates, and hence some thermodynamic quantities like heat capacity here. So this problem is just to illustrate that just simple dimensional analysis, like which is simply what we did here, to to uh, to find how the volume of this phase space region depends on the energy. So this simple dimensional analysis is sufficient, and we need not like do these integrals to find the volume and all. To calculate, let's say, the heat capacity, this alpha is not required if we just want to calculate only heat capacity, like I mentioned. Yeah, so this is with some different potential, and yeah, this problem illustrates how we can calculate uh, let's say the heat capacity in this case. Sorry. I'm sorry. Yeah, all right, so let's then actually move on to the next problem. Yeah, so so in anticipation of the coming problem, the next problem, we have a simple counting question here, uh, and we're going to use the result of this problem in the next question to calculate the number of microstates. So yeah, so this is very simply stated. So so there is a basket of fruits, and there are fruits of different kinds. So there are fruits of R types, to be precise, like there are apples. So let's say these are all apples, and these are all oranges, and mangoes, and so on. Like there are some other, like, yeah, there are different kinds of fruits, all in abundance. I mean, there's no shortage, and we have to pick k fruits from these sort of fruits, and the question is about the number of different ways of doing this. So notice that the order of fruits picked doesn't matter. So what makes uh, uh, what makes one choice different from the other is the distribution among different fruits. So if n1 is the number of fruits of type 1, this is the number of fruits. Okay, let me try to. Yeah, so n1 is the number of fruits of type 1, and n2 is the number of fruits of type 2, and so on. So all these numbers must add up to the total number of fruits that we have to pick, which is equal to k. So this problem can also be stated as finding the number of non-negative integer solutions to this equation. So a particular fruit can be picked 0 times, or like not picked at all. So each ni can go from 0, 1, and so on. So this is the this is one way of writing the same question. Which is the number of solutions of this equation. Okay, so yeah, so we can it's a standard, like, popular question in combinatorics. So we can think of it like this. So it goes like this. We can try to arrange let's say all the fruits of one type in a straight line. So let's say we are going to arrange all the oranges first, and then all the apples next, and all the mangoes next, and so on. We can try to imagine doing this, or equivalently, if we like demarcate the boundary, or the place where we change the type of fruit with some bar, we can, we can draw some bars between fruits of different kinds. So then it is sufficient to just like just label all these with some dots. So okay, sorry, this is not like exactly corresponding to the above picture. So okay, yeah, and so on. So so from this picture, it is understood that there are 3 oranges, 2 apples, 3 mangoes, and so on. So so we can map any uh, fruit pick, or like we can map any choice of picking the fruits to this this way of like picturizing the number of fruits of each kind. So there's a one-to-one mapping between each of these ways of denoting things. So so this is like the number of ways of having k dots. So the total fruits we must have is k, and r minus 1 bars. So if we have, let's say, 4 fruits, then we'll have 4 such containers, or baskets, and there would be 3 bars separating these 4 slots or columns. So there would be r minus 1 bars, and any way of so we can arrange these k bars and r minus 1 bars in a straight line, and that would correspond to a particular way of picking the fruits, like a particular way of choosing the fruits, and vice versa. Any particular way of choosing the fruits would correspond to some way of arranging these dots and bars in a straight line. So we can simply calculate the number of the ways of arranging these bars and dots. So yeah, it is like a simple uh, calculation in permuting things. So we have these we have k plus r minus 1 objects in total, and k objects of one kind and r minus 1 objects of the other kind, which are dots and bars respectively. So it's going to be k factorial by r minus 1 factorial, or this is going to be k plus r minus 1 c ck, or cr minus 1, yeah, ck. Yeah, so this is the answer to this problem. Yeah, like I said, it's a very popular problem in popular and like standard problem in combinatorics. But for us, it's going to be useful to do the next problem, to do the counting in some very interesting physical system. Okay, so let's move on to that without any. All right, so the system we are going to consider is a system of n atoms. So there is a system with n atoms, and by atom I don't actually mean like a real physical atom, but something which has this energy level spacing, or this energy these energy levels. So in this case, each atom or each object in this case, so there are n such objects. Each object is each object has this energy level spectrum, or so it has these as the possible energies. So the lowest energy state is going to be 0. The next available energy for this object is epsilon. The next energy is 2 epsilon, and so on. So, and there are n such atoms in the system, and the system is isolated. So like if you have already seen this, so this spectrum is similar to that of quantum harmonic oscillator. So this problem tries to find the occupation number in some particular level from the microcanonical formalism. Yeah, but if you're not like familiar with that, like don't worry about it. So just treat it like some microcanonical ensemble problem. So yeah, so also I should mention that like since I've made this remark, so yeah, for the quantum harmonic oscillator there is like there's a 0 point energy which is going to shift the energy by some constant which is like half h bar omega. But yeah, but sorry, so don't worry, like we need not worry about that. So this is some object with this constant energy level spacing, and of course it has it is bounded from below. I mean there is like the lowest energy is 0. So that we can write the total energy of this of the system as the sum of energies of these individual objects. So let's say the first atom is in nth state. let's say Ni be the energy, the level of, or let me say, uh, yeah, level of, yeah, so it is a state in which ith atom is present in, yeah, so this is a state of ith object or atom. So then the energy of the ith atom is, or ith object is going to be Ni times epsilon. And the total energy is a sum of these energies, so that is going to be sum over I Ni times epsilon. So yeah, so obviously this E has to be a multiple, it has to be an integer multiple of epsilon. So let us assume that E by epsilon is an integer. I mean, only such E's are allowed in the first place. So let us consider such E and say that the system is isolated and its total energy is fixed to this E. And again, the story is the same. What is the number of microstates of this of the system at this energy? So sum over I Ni is going to be is going to be E by epsilon, where each Ni can be non-negative integer. So this is exactly the problem that we saw before, the problem of fruit picking. So yeah, like the number of solutions to this equation is simply the number of microstates that we need here. So omega of E and N is simply going to be this answer that we derived here, this k plus r minus 1 ck. So if in using the notation of the previous problem, r, which is the number of which is the number of types of fruits in the previous problem, that would be the number of atoms here, or the number of the number of these objects. So r is going to be n, and k is epsilon by E, which is, like we discussed, is an integer. So yeah, so then that is going to be yeah, so it is going to be, I think, yeah, k plus yeah, so epsilon by E plus n minus 1 c n minus 1, which is going to be this factorial by, sorry, divided by n minus 1 factorial and this. Yes, so yeah, very good. So this is the number of microstates that we need, and now the next part of the problem is to find the temperature of the system in terms of energy, or vice, or equivalently expressing the energy in terms of the temperature. So yeah, this is again the usual for the standard crunching in the microcanonical ensemble. So this S is going to be ln omega, and yeah, so here since we are interested in the thermodynamic limit anyway, we can use the Stirling's approximation, which says ln n factorial is n log n minus n. This is a leading contribution to log n factorial. So we can use this Stirling approximation to simplify this further. Yeah, so this S is going to be epsilon by E plus n minus 1 . Actually, okay, yeah, let's simply do this. Yeah, so after using the Stirling's approximation, that this becomes so these things are going to cancel. Yeah, so finally this is going to be minus n minus 1 ln n minus 1 minus, yeah, so yeah, this is the entropy, and what we need is the temperature. So if you can quickly calculate that, oh sorry, yeah, there is yeah, 1 plus yeah, this is what would become of the first term, and the second term would be yeah, so finally we have this, we can express this compactly as so 1 plus ln of 1 plus epsilon n by E, I think that is correct, yeah, minus sorry, yeah, my epsilons and e's look the same, sorry, yeah, this is epsilon, so that's going to be 1 plus yeah, n epsilon by E. Of course we have this epsilon by E term, but E is extensive, and so in the thermodynamic limit this term would go away, so this E, but there would be this term epsilon by E, yeah, but in the thermodynamic limit E would be proportional to N, or we can drop this term. Yes, yeah. So then epsilon or e to the epsilon by t is going to be 1 plus n epsilon by e. So n by e is going to be n by e is going to be yeah, 1 over epsilon e to the epsilon by t minus 1, or yeah, I'm sorry if my epsilons and e's are looking the same. Yeah, so finally the energy per atom, or the energy per object, is epsilon by e to the epsilon by t minus 1. Yeah, so this is the total energy per particle in the thermodynamic limit. Yes, so this looks right. So this is the so we have calculated the number of microstates first of all, and then use the Stirling's approximation, the standard way to approximate factorials, and then from that we derived the temperature. So so this is actually the first example that we did in these set of problems, where we actually counted discrete set of states. So in this previous problem, we calculated the phase space volume uh, to get the number of microstates. But here it is indeed actually directly the number of microstates, like the discrete. Uh, so here the states allowed are actually discrete. So uh, we will sorry. So hopefully in the like in the upcoming weeks, we'll do this calculation, or in the upcoming lectures from the course, you will see this being derived in another formalism. But anyway, it's a good exercise to do it in this ensemble as well. Okay, so if there are no questions, let's move to the next problem. So here we have an ultra relativistic gas of particles, classical particles, in 3 dimensions. So by ultra relativistic, what we mean is that the kinetic energy is much greater than the rest mass energy of the particles. So the kinetic energy, so the total energy would be of a single particle. So this is this energy of a single particle, p square c square plus square c to the 4. So the rest mass energy, or rather the kinetic energy, is much greater than the rest mass energy. So the kinetic energy is actually this minus the rest mass energy. So in the limit where this is much greater than the rest mass energy, so this Ke is simply, it is approximately equal to Pc, to leading order. So this is what we have in this problem. So So we can assume to start with saying that, so there are a bunch of particles in some box, in some container at fixed energy, where the kinetic energy of each particle depends on its momentum like this. We can just say this is like the starting point. I mean, like there are such particles. So they can arise in this ultra-relativistic limit, or there might be other situations in which these particles may arise or emerge. But let's say it is given that there are such particles, and the problem or the task is to find uh, to calculate the thermodynamics, or to find the thermodynamics of this gas of particles. And since we are doing microcanonical ensemble this week, so why not try to do the like thermodynamics in this formalism. Okay, so yeah, so this like the calculation is not going to be very different from the second problem that we solved today, because again it's we have a phase space, like a continuum phase space, and we'll have to find the volume of this phase space, and again it will turn out that it is sufficient to find out how the volume scales with the energy and the number of particles. So yeah, so let's get to it. So the total, so before we write the energy, the phase space for this problem is a set of all position and momenta of all the n particles. So each vector here has 3 components. So it is going to be a 6-dimensional phase space. Phase space. Okay, so and the total energy, the energy function is going to be sum over I mod pi bar times C. That is, I mean, there are no interactions. This is yeah, sorry, I might have like forgotten to emphasize this or mention this. Yeah, this is an ideal relativistic ideal gas with this dispersion. So there are no interactions. There is no potential energy for the interactions, or there is no other external potential. So this is the energy function of the system, and we'll have to find the volume of the region which corresponds to the energy being less than some value E naught. So yeah, I mean we have to calculate that. So so this E, okay, let me use a different symbol. I'm sorry. So this E has no dependence on xi. So when we integrate over the xi coordinates, the spatial coordinates part of the phase space, so integral d3 xi product over I from 1 to n, this is simply going to give us volume raised to the power n, like just like in the standard ideal gas. This is no different. Where it would differ is the momentum integral. Yeah, I mean actually we do not need to do the integral, but the phase space volume coming from the momentum variables. So let us consider, this equation: E naught is equal to, or E naught by C is equal to sum over I mod pi bar, which is equal to this, or rather sum over all such expressions, such quantities. Yeah, so this equation defines a surface for us in the 3n dimension, in the yeah. So this defines the surface in a 3n dimensional space, and we need the volume enclosed by the surface. So we can again do like the same kind of like the dimensional analysis that we did, and try to estimate the dimensions of this object, this volume object, in various directions. So yeah, so if you look at where this surface intersects, let's say the P1x axis, uh, that is simply going to be E by C, I think. Yeah, that is simply going to be E by C, or E naught by C. So this is a point where, okay, P1x is non-zero, and every one of these uh, variables are zero. So this is on the P1 axis, P1x axis. Yeah, so and this point, this dimension is E naught by C. So we have a similar picture in every other direction. So the total volume, this volume of as a function of E naught, that is going to again be proportional to the product of dimensions in various directions. Of course, again we have some unknown, some quantity here, alpha of n, but we have E naught by C to the power 3n, because we have 3n directions in this space, and we have of course we have the volume, this first factor coming from the uh, spatial coordinates part, this integral, we have this volume. So yeah, this is the volume enclosed by the phase space, sorry, volume of the phase space that we need, and the number of microstates is can be gotten simply by dividing this with the appropriate dimension full thing. So that is going to be is this. Oh no, sorry, I think it is just 3n. Yeah, so we can just write this as hc to the power 3n. Yeah, and then we can actually find the equation of state from this. We can find the heat capacity and so on. So we can basically find like the thermodynamics of this gas. So what is being asked is the ratio of heat capacities. So yeah, so let's try to find the equations of state. So 1 over T is So first of all, the entropy is um, something. I mean, this is a some constant which doesn't depend on volume and energy, plus n ln v plus 3n ln e. So 1 over t is simply 3n by e, or e is 3n times t. So this is how the energy of the gas depends on temperature, and we can also find the pressure like the other equation of state. The pressure is going to be dou s by or p by t is going to be yeah, dou s by dou v at constant n and e, so which is going to be n by v. So pv is equal to n times t. So this yeah, so this equation of state is again the same for this ideal gas as well. So this just simply follows from the fact that there are no interactions, and we can separate out the volume integral like this. I mean, we can separate out uh, the integral over the position coordinates like this, and we get a factor of v to the n. So this equation of state directly follows from the fact that there are no interactions, but the fact that we change the dispersion of these particles, like the kinetic energy dependence on the momentum, the fact that that has been changed will of course change the heat capacity or the energy. So energy is going to be 3 nt. Yeah, so we got these equations. These describe the thermodynamics of this gas, and what we need is the ratio of heat capacities. So yeah, CV is going to be simply dou E by dou T at constant volume. So yeah, so this is simply going to be 3n, and because of this equation, because of the equation of ideal gas, so ideal gas equation of state, so this implies that Cp and Cv have to differ by n. Yeah, so these are the total heat capacities, not in these are not intensive heat capacities. So n is the total number of particles. So Cp is going to be 4n. Like I said, these are not intensive specific. These are not specific heat capacities. These are total heat capacities. And similarly, this is also the total. Yeah, or of course, if we want the intensive per particle capacities, these are 3 and 4 respectively. Yeah, anyway, the ratio of these heat capacities is 4 by 3. Yeah, so for a monoatomic ideal gas with the standard dispersion, or like the quadratic dispersion for the kinetic energy, the gamma is 5 over 3. Yeah, but here it is 4 over 3. So of course this is directly a result of the kinetic energy depending as mod p. Yeah, so this is how uh, like if you can say the microscopics, so can of course alter like or influence the thermodynamics. I mean, this is like one example where we just where we did the calculation and saw this. Okay, so if, okay, let's move on to the next question. Yeah, so in this problem we have some model of a solid of a of a solid where you have these atoms, n atoms, in a three-dimensional solid. Okay, let me just write like n atoms, and so the model is as follows. So the model is that every atom can be in two states with energy 0 or epsilon. Uh, and uh, we have a bunch of these atoms, n atoms. And interesting thing here is that this epsilon, the energy of the excited state of an atom, that depends on the volume of the full solid. So this E depends on the density of the solid. That is the model. Let me finish writing this and comment uh, on this model. So epsilon is a function of V over N. It is A by V by N to the power gamma. So the excited state of or the excitation energy of a particular atom depends on the density of the solid. This is the model, and this can be thought of as a particular limit of uh, the Einstein solid model. So like if you're interested to know more about this model, so this is like some low temperature limit of the Einstein model. So in the Einstein model we would have infinitely many uh, states for a particular atom, equally spaced uh, levels for each atom. And in this model only the ground state and the first excited state are kept and the rest are thrown. So this would apply, I mean this would be like a low temperature limit of that. Yeah, but we don't need to worry about this further. uh, so I mean to illustrate this uh, formalism or the methodology of doing calculations in the calculations in the microcanonical ensemble, uh, we can uh, we can simply like uh, do the crunching and see uh, how to derive the various quantities. So yeah, so this is this is a two-state system at each atom or each site. So yeah, so you might have already encountered this before, the two-state system in the microcanonical ensemble. So the number of microstates depends on the energy like this. Uh, so we have to select e number of atoms and place them in the excited state, or e by epsilon number of atoms and place them in the excited state. So that would be n choose e by epsilon. So there is going to be n factorial by n minus e by epsilon whole factorial times epsilon by e whole factorial. Yeah, so and entropy would be then n log n minus epsilon by e by epsilon ln this thing epsilon by epsilon. This is after Stirling's approximation has been used, would be used. Yeah, so this is the entropy as a function of E, and what we have differently in this problem compared to just a two-state uh, just a two-level problem is that this epsilon depends on the density volume. So epsilon is a function of v over n, and like we have written it is a times uh, n to the gamma by v to the gamma. So this depends on the volume, actually epsilon depends on the volume, and let us look at this dependence. Dou epsilon by dou v is going to be minus gamma a n to the gamma by v to the gamma plus 1, or that is equal to minus gamma by v times epsilon. Yeah, so this is the derivative of this parameter epsilon with respect to volume in terms of this parameter gamma, which is called the Grunisian parameter. So we now have to think of this expression for entropy uh, by saying that this epsilon here is indeed a function of volume. So there's a dependence on volume for entropy through this epsilon. Okay, so that is the main point of this question, and like when it comes to calculating the equation of state. So 1 by t is again dou s by dou e, so uh, we can write this as yeah, it is going to look very similar to what we did. Okay, so it's going to be minus yeah, minus uh, Okay, so minus minus epsilon times, yeah, it is going to be yeah, okay, let's worry about the minus later. Yeah, so it's minus of um, minus 1 over epsilon, yes, and ln of this thing times minus 1 over epsilon, so it's going to be this, yeah, and yeah, this is going to be 1 over epsilon, yeah, plus ln epsilon e by epsilon. Yeah, so okay, finally this is going to be 1 by epsilon times log n epsilon by e minus 1, or epsilon, yeah, e to the epsilon by t is plus 1 is equal to n epsilon by e, or e by n is going to be epsilon by 1 plus e to the epsilon by t. Yeah, so okay, this is of course the same expression that we just get for a two-state system. So here of course there's a dependence of epsilon on v. So yeah, just to make this point, so here epsilon is a function of v and n, is a function of v over n, and what we then need is the pressure in this question. So calculate the pressure as a function of the density or the specific volume and temperature. Yeah, so P by T is going to be dou S by dou V. This is what we'll be using. Yeah, so that can be, yeah, calculated from this. So here we have to remember that epsilon now is a function of volume. So yeah, again, just taking the derivative, nothing more fancy. We would get something like um, minus e times, so it's going to be 1 by epsilon square dou epsilon by dou v, I think, yeah. Yeah, plus log of n minus epsilon by e plus e by epsilon square times that, and similarly the second term would be yeah minus 1 over epsilon square uh, yeah yeah dou epsilon by dou v plus log of that Yeah, so this is just some yeah, just taking derivative, and then we can simplify this now to see that this is going to be e by epsilon square dou epsilon by dou v times log epsilon by e divided by, did I get this right? The minus sign, yeah, it looks like that. So it is n minus, sorry, yeah, this is epsilon by e. Yeah, epsilon by e divided by n minus e by epsilon. Yes, so yeah, so just to make sure that this is correct, so we have yeah, yeah, that's fine. Yeah, yeah, so p by t is dou s by dou v, and uh, we can substitute for epsilon here. That is going to be minus gamma epsilon by v. So e by epsilon gamma by v times ln n epsilon by e minus 1. So this is going to be p by t, and we have 1 over t here. So we can simply divide this to get rid of this factor. Yeah, so then p would be so p would be epsilon e. So this log term is going to be cancelled, and epsilon p is going to be e gamma by v. So this is, I mean, when expressed in terms of energy, but yeah, so energy is going to be epsilon n by this factor. Yeah, so finally we have it as gamma times gamma by v tilde uh, yes, yeah, so finally we were able to express the pressure in terms of whatever is required. Yeah, so okay, so to summarize the calculation of this uh, in this problem, so we have in this problem the excitation energy of this atom, that indeed depends on the volume of the solid, and yeah, and that gives rise to uh, like a dependence of this entropy on the volume. So okay, so we can move on to the next problem. Yeah, so let us now discuss discuss a statistical mechanics model of a rubber band. So this discussion is from this textbook by Herbert Callan. So yeah, of course, you feel free to go and refer to the textbook and read the discussion. So since we have uh, done some problems using the microcanonical ensemble formalism, uh, yeah, so let's try to understand the physics of a rubber band and how to model it uh, and try to see if we can extract some physical information, like some physics of the rubber band that we see in the I mean, that we see in our day-to-day lives. So first to start off with like a thermodynamic description, or like a phenomenological description of the rubber band. So one striking property of the rubber band is that if you increase the temperature, it shrinks, it contracts. So consider the following experiment. So there is a rubber band which is uh, stretched, and it is tied at a fixed length. This is a phenomenology of rubber band. What we know from experiments, what we observe, is that if you take a if you take a rubber band and uh, tie this at some fixed length, stretch it tight at some fixed length, and uh, increase the temperature of this rubber band. So you can heat it, let's say try to increase the temperature. Yeah. So in a world where that is a candle, this rubber band will be heated. Now the question is, what happens to the tension of the rubber band? So we have stretched this rubber band, so it is at a tension, and after heating it, after increasing the temperature, what happens to the tension? So does it increase or decrease? So to be precise, what is this quantity? What is okay, sorry, let me use a different symbol for tension. Yeah, nothing to tensed about. So let's use cal T, or this some fancy T for tension. Yeah, so this is tension, and T is the standard T is for temperature. So that we don't have to get confused, let us use this fancy T for tension. And the quantity we're interested in is how does the tension change as you change temperature, dou tension by dou T, at a fixed length. So we are fixing the length of this rubber band in this experiment. So is this positive or negative, first of all? So is this positive or negative? Okay, so if this were like some thin metallic wire which we stretched to bring about the tension and heated, then we would expect that this metal would expand on heating, and thus thus the temperature and thus the tension would decrease. If this were a metal wire, thin metal wire. then this quantity would be negative. So then dou tension by dou T at constant length will be negative. So once you heat the wire, I mean, it would want to expand. I mean, but this is at a constant length, so so the tension would be like relaxed a bit. Yes, that's right. Yeah. So we would expect that this quantity is negative if this were like a metal wire. But what we observe with the rubber band is that the opposite happens. So it's as if it would try to shrink or contract if you heat it. So for it to maintain this length, the tension would have to increase. So dou tension by dou T at this constant length is positive. This is what we observe from experiments. Okay. So how is a rubber band different from metallic wire? Like microscopically, for these strikingly different thermodynamics to come into play, how is the rubber band so different from a metallic wire microscopically? Okay, so we will try to look at a model of like a very simple model of a rubber band and try to explain, you know, this observation. So before we go on to the microscopic model of the rubber band, let us simply like use some Maxwell relation and relate this to some other quantity. So that will actually be quite useful when we write the thermodynamic model and do the interpretation. So we have this. So for the rubber band, we can write du is TdS plus TdL. So remember, this is not tensile. This this is not compressive. So tension is it's a force trying to stretch the rubber band. So there would be a plus here. So and then we can define the free energy F as U minus ds. So dF would be minus S dt plus tension dl. All right, so so S is minus dou F by dou T at constant length, and tension is dou F by dou L at constant temperature. And we can derive a Maxwell relation from this free energy using the fact that the second derivative is symmetric for the smooth function. So that would mean that yeah, okay, let us write it this way. So that would mean that dou S by dou L at constant temperature is equal to dou tension by dou temperature at constant length. Yeah, so this is the Maxwell's equation you get. So this quantity that we are interested in, you know, how the tension changes with the change in temperature at constant length, that can also be related to this change of entropy with length at constant temperature using a Maxwell's equation. So we'll see, we can like we can get a sense of this quantity on the left hand side from our microscopic model, and we can then say something about the quantity that we are interested in. So okay, yeah, let's without any delay, let's look at this microscopic model. So we know that rubber band uh, is it's a polymeric material, or it's made of polymers, long chain polymers. Right, so there are monomers, which are the basic building blocks of these polymers, and uh, and the physics of polymers comes about because of the various ways in which these monomers can arrange themselves in space, in various uh, in various uh, in various ways. Monomers, they can orient themselves, they can orient in different ways. I mean, they can orient in different ways, and we'll see how this plays a role in uh, in deciding whether this quantity is positive or negative. So let's say we have uh, like a bunch of monomers, and they can uh, orient either in like the x direction or the y direction. Yeah, this is a very simplified model, which nonetheless captures uh, some features of the rubber band. So this yeah, sorry. So these monomers can orient either in x direction or y direction. So they can take turns. So they can be turns like this, and so on. Yeah, so uh, it can have this sort of orientation. Uh, so these are all allowed microstates. We say that the monomer is in the plus x direction if it is going to the right. So this is plus x. This is also plus x oriented monomer, whereas this one is a minus x oriented monomer. And similarly for the y direction, this is a plus y oriented monomer. This is a minus y oriented monomer, and so on. So so in this model, only these two orthogonal directions are allowed, but yeah, that will be enough to explain the physics, like at least the physics that we are interested in, or we want to explain. Uh, so a general configuration will involve like some certain number of monomers in the uh, plus x direction, which are oriented in the plus x direction and minus x direction, and so on. So the total number of monomers is n. So all these must sum to n. And the important ingredient here is that uh, uh, yeah, sorry. So of course, so this rubber band is at a tension. So I mean, we can apply tension to this rubber band. sorry, this is cal T. So there is no tension in the y direction, so we are pulling, we're thinking of pulling this rubber band in this x direction. So note that these tensions are not the independent variable, the basic independent variables of microcanonical ensemble. These will be like the derived thermodynamic quantities in the microcanonical ensemble. These tensions, yeah, but of course, what is a natural variable in the microcanonical ensemble is the total energy of the system E, and of course the lengths. So these are fixed in this formalism, and n of course is fixed. These are fixed in the microcanonical ensemble. And we can express these thermodynamic quantities, I mean these variables of the microcanonical ensemble, in terms of the microscopic details like nx plus, nx minus, and these four numbers. So n is that which we've already written here, and Lx is going to be nx plus minus nx minus, and Ly is going to be ny plus minus ny minus. And importantly, the energy, yeah, we have not talked about the energy of configuration. So the key ingredient here is the statement that some energy cost has to be paid if the monomers orient in the plus or minus y directions. So there'll be some energy cost, or there'll be some loss of energy. Yeah, so there'll be at some places where there are monomers, there'll be some loss of energy, like minimization or something, so some interactions lost, so that if there's a monomer oriented vertically, it will cost some energy. So plus or minus y monomers, they cost energy. So the energy is going to be epsilon. So let's say this energy is epsilon times ny plus ny minus. Okay, so we have all these we have all the required relations of these microcanonical ensemble parameters in terms of these microscopic variables. So the entropy the number of microstates is simply the number of ways of having all these different combinations of these four numbers, which would correspond to different orientations. So that would be n factorial by nx plus factorial times nx minus factorial times ny plus factorial times ny minus factorial. Yeah, and so from the we can express all these in terms of we can solve for nx plus these four numbers in terms of the the parameters of the ensemble. So there are four equations, and you can solve for these in terms of the parameters. So finally we can get the entropy in terms of as a function of E, Lx, Ly, and N. So this can be calculated from ln omega, so that that can be done. But in the interest of time, I'm not going to do this calculation here. But what will be of interest to us is how the entropy depends on the length of the rubber band. Okay, so first of all, setting the tension in the y direction to 0 gives us the condition that Ly is 0. Right, so which just means that the rubber band lies completely, let's say, on the x-axis. So that is what we need. So we can also define, we can derive tension from this as the derivative of this with respect to Lx. So these can be calculated, and like I said, because of the time factor, like let us instead look at the like the dependence of entropy on the length. Okay, so when we let us just consider the like a qualitative picture. So if you have a rubber band of this length, let's say so let's say L is equal to N. So that means Nx plus is equal to N, and Nx minus is 0. So simply all the monomers are oriented in the same direction. So this is a maximum length that you can have. But such a configuration, or like if you want to so if you want to have this this maximum length, then there is only one microscopic way in which you can achieve this. Only one microscopic state with the total length being equal to N. Yeah, of course. Sorry if I've forgotten to mention. Like here in this way of writing, the each monomer has unit length. So yeah, the maximum length is equal to the number of monomers itself. So that is what we have at maximum length. There is only one micro state, only one microscopic state consistent with that. But instead, if you consider a length which is less than the maximum length, so this L is less than L max, which is N. So then there would be many more ways of having this length possible. So there can be something like this. All the so there are many microstates possible. So that means the this quantity, if you decrease the length, then the entropy will increase. I mean, like there are more microscopic configurations possible with a smaller length than with a larger length. So once we go to this quantity, look at this quantity. So dou T by dou L, I mean dou tension by dou T, which is what we want at constant length, which is equal to dou S by dou L at constant temperature. This is going to be positive. Yeah, hope I yeah, sorry, I got a minus. Yeah, this is a minus here. Yeah, so I said yeah, yeah, whatever I said in words is correct, but yeah, as you decrease the length, the number of possible microstates will increase. So dou s by dou l is negative, and this thing is actually equal to minus dou s by dou l at constant temperature. So this is going to be positive. So yeah, as you see, if you increase temperature, the tension will increase. So it will get more stiff if you heat the rubber band, or uh, like if you do this experiment at a constant tension. So let's say if you hang a weight to a rubber band, then if you heat it, then the length will decrease. So the thermal expansion coefficient would be negative, or equivalently, like we discussed in this way of doing the experiment, at constant length the tension will increase if you increase the temperature. So this is a thermal expansion coefficient. It will be negative. So yeah, uh, to quickly summarize the like the physics of uh, this problem. So the rubber band will have more entropy, more ways of being consistent with uh, the macro state if the length is smaller. So at a smaller length, it can wriggle and do a lot of things and have the same length in many ways. So the entropy would be more. So if you heat a rubber band, that's why uh, it would uh, it would shrink, because it would gain entropy by doing so. Like it would gain entropy uh, by contracting to a lower length. Yes. So yeah, this model of the rubber band explains, at least this feature, this phenomenological observation or fact. Yeah, so this is how, I mean, like this is one example of trying to understand like the phenomenology from a simple microscopic model. uh, yeah, so yeah, hopefully that made some sense. Okay. Yeah, so yeah, thanks a lot. So let us stop for today and see you next week.